Hello and welcome to Toddcast number 23. I'm hoping to tie up the stereochemistry section with this one, so we'll see how it goes. So far, we talked about different types of isomers. Specifically, last Toddcast was stereoisomers, and we focused on carbons with 4 different substituents. We're going to continue down that path because it leads us into biology. So this one sort of ties off the last of OChem and then transitions into bio and biochemistry and how we apply it there. So properties of enantiomers, just want to point out, enantiomers, non-superimposable mirror images. So just reiterating that. So in this case, if it has a chiral center, if I drew a mirror here, then it would look like this. But I also know I can draw it by just simply changing any 2 substituents. So if I change the OH and the H, to put the OH in back, and the H in front. So I'm either going to call it an enantiomer because I see a mirror image, or I'm going to call it an enantiomer because I changed 2 substituents. The H went back or in front, the OH went back. Either way, it's the same difference. So when you only have 1 chiral center, it works out that way. And that's going to be an advantage. We'll look at this down the road as well, that enantiomers are mirror images, but they're also stereoisomers where all the chiral centers differ. Okay, so the one I've drawn here, as you can see, is the one that has the 2 substituents switched. So you can't see the mirrors, but they are enantiomers because one is R and one is S. So just to check real quick, priority 1, 2, 3. So we have R on the right, or left, excuse me, that was bad. And then H in front, so priority 1, the O, 2, 3, so O to ethyl to methyl. Clockwise, because H is in front, S. I'll elaborate on that in a little bit. But the key thing to care about here is because they are enantiomers, and you know what, I will put the fact this is R, and this is S, of the same compound. So S-2-butanol, R-2-butanol, their boiling points are the same. And notice the numbers aren't listed the same. And this is because this is taken from experimental data. Just to emphasize, not everything works out perfectly. So if you've learned anything in lab, you've learned that it's so great in theory, but when you start seeing it in practice, there are occasionally some glitches. So this is a case where 97 to 100 and 98 to 100, that's the same boiling point. The densities, this is within the area of research, they're the same density. This is the one that should catch your attention. This alpha D, we haven't looked at it yet, but it's an interaction with light. D stands for sodium light. And so as you perhaps have learned in general chemistry, from Beer's law, absorbance equals ECl. E is in constant for the molar absorptivity of a compound. C is the concentration of molarity, and L is the length. So any interaction with light depends on these values, the length of the cuvette you're sending light through, the concentration of whatever's in there, and some constant for that material at a given wavelength. And so that's what this D is. It represents light of a very specific wavelength, and that wavelength is used to measure how it interacts with light. So asymmetric compounds will behave differently with plane polarized light. So because it's asymmetric, it has more electrons on one side than the other, which means it has asymmetric magnetism. So the magnetic plane of light can interact with it, and in doing so rotate. And so for this R, it rotates negative 13.52 degrees over a given distance, which we'll define when we start looking at polarimetry. And then the S, which does the exact opposite, rotates in the clockwise or positive 13.52 degree direction, when again, given the exact same conditions, same cuvette length, same concentration, same wavelength of light. Okay, so the point being then, optical isomers, they interact with light, specifically enantiomers, have exact opposite interactions. So polarized light, let's talk about what that is. So this is coming out of physics, and my assumption is you haven't taken optics yet in physics, or if you are taking physics concurrently, you haven't gotten there yet. So let me at least emphasize what we mean by this. The electric wave, so all light has a magnetic wave and electric wave. So electric wave, let's say, is in the vertical direction. There is a corresponding, I want to say induced, it's not quite the word I'm looking for, magnetic wave that is, didn't want to do that in the last line. So not sure if this makes sense what's going on, but it's a perpendicular wave. So we have the red wave in the XY plane. Let's just call the sheet of your paper or the screen XY. And then the magnetic wave is in the XZ plane. So it's going in, then coming out, and going in and coming out, going and coming out. So plain polarized light is where you have a filter, usually made of a plastic that's some plastic polymer, where everything is aligned and crystallized in a way where it's all vertical. So whether we consider filtering the magnetic or electric wave doesn't really matter. So by convention, we usually consider the E wave. So the E wave can be vertical, but it could be horizontal, it could be every which way. So I'm going to ignore the magnetic wave and just focus on the electric wave at this point. So these arrows represent the orientation. So this one here would be the one straight up or straight down, one going in and out, and there would be different ways. When you send it through this filter, only the vertical components go through. So we have this, and then notice how this B is perpendicular. That's a wave I just erased. It goes this way. So it filters by E or B, whatever you want to call it, but I'm going to say it filters by E, and B subsequently is an induced, like charge and motion creates a magnetic field. So electric wave will create the B wave. So that's why we consider the E. So it goes through in a plane polarized fashion, meaning all the E waves are perfectly vertical. So any horizontal got filtered out, didn't pass through. So just as a point of interest, with sunlight, perfectly randomized light, 50% will get through, 50% will be filtered, meaning it's equally as likely to be vertical as it is horizontal. Okay, so with that in mind, here's what we do to take advantage of this. Polarized light can pass through another polarizing plate without losing intensity, meaning if I put a second plate exactly up like this, so if I had another plate here that's perfectly in line with it, the plane polarized light would continue to pass through it. But if you rotate it by 90 degrees, so you have one vertical polarizer and one horizontal, you don't see anything. I'll leave it to physics to explain how that works and why that works and what cool devices such as 3D films we can take advantage of this with. But how we use it in chem is we take advantage of putting our compound in this region right there. So slightly different picture. This is, instead of all the random waves, instead of drawing the wave going through, I'm just going to do it like this. So if the first wave to get through is like this, aligned with that polarizer, that first polarizer, so I want to draw it in line with that. Hopefully my picture is kind of okay. I'm going to stop it there because it starts to get punky. What happens is, if in this region right here, in this space between here, I have a tube full of my solution, my compound, it will actually interact with it and cause this wave to start to rotate. And to let the light out completely, I have to take this. Here's my first polarizer. Notice the second polarizer is slightly a different angle. So if this happens, again, I'm going to erase all my stuff. I want to emphasize that this polarizer is like this one's like this. Because I had to rotate the second one to let the light out of my sample that was in here, they refer to these two lines by their angle. So notice this one had to rotate. So if I put them on top of each other, this one had to rotate, this polarizer had to rotate, let's say, by, I don't know, 20 degrees, 30 degrees. Totally arbitrary, but if I'm looking from this sight line, I'm going to say it rotated clockwise 20, even though from my perspective, I'm at the other end, it looks like counterclockwise. But convention is what it is. I'm not going to worry about convention. I'm going to worry about magnitude. So I put them there. This is about a 20-degree angle. That'd be your optical rotation. That'd be what we call the alpha D. Okay. Now, we're going to eventually call it the specific rotation because, again, it depends on concentration, depends on other factors. So we want to have specific conditions so that we can compare equally across all compounds. So what I'm calling optical rotation is an uncalculated or tethered number, one that I haven't put through the standards. But when I convert it into a standard, we'll refer to it as a standard. So it makes sense. If we standardize it, it'll be standard. So polarimeter. This, I hope, I don't know if my drawing does a good justice to it, but here's the wave vertical, comes in vertical, but the compound starts to rotate it. And it's, again, I don't know if this is doing a good job, but this is starting to come up a little bit. and it's twisting. So you kind of see it with this wave not being horizontal and not being vertical, kind of somewhere in between. So we had to rotate this second polarizer by a certain amount. That's the same thing we were saying before. Hard to visualize. My artistic skills make it even worse, but hopefully you understand the concept. It's rotating. So specific rotation, based on the standards, is the observed rotation that we read out of here, but then we divide it by the length. And so standard cuvette is 1 decimeter. You usually, in real life practice, don't have to worry about that one too much because all the devices are made 1 decimeter because it's standard. Why use a non-standard thing and have to do math when you can just use the right one? Concentration is actually in units of grams per milliliter, not molarity. So we base it on just the measurable thing without having to do math. So OChem, we're dodging a little bit of math, but if the concentration is like the standard 1 gram per milliliter, and it's 1 decimeter, then dividing by 1, or observed rotation is what it is. So typically, we try to do the observed rotation with 1 gram and a milliliter of solvent, and then put it in a cuvette of a certain length. The problem comes in, not all compounds are that soluble, so sometimes the concentration is a little bit lower, so the rotation is going to be a little bit lower, and so you have to divide and factor it out. Okay, that aside, I'm never going to worry about that number, how we generate it, just going to worry about how we use it. Okay, so polarimetry questions. Any sample rotates plane polarized light is called optically active. So this phrase, you're either active or inactive. You either rotate light or you don't rotate light. To rotate light, you must have a chiral center. A sample that doesn't have a chiral center is asymmetric, or is perfectly symmetric, doesn't have an asymmetric center, doesn't have stereogenic carbons, is called optically inactive. Fair enough, kind of creative. A pure sample of a compound is optically active and rotate plane polarized light. True. A chiral compound will be optically inactive. A chiral compound will be active. Okay, so those two sort of go hand in hand. The observed rotation is what we measure. The standardized one is what we divide through. So that is what we just looked at on the other one. We put alpha, the observed rotation, divided by concentration in grams per milliliter, and then the length in decimeters. So this is the so-called standardized measurement called the specific rotation. I'm going to use these interchangeably because, practically speaking, in lab, we usually do the right concentration and the right length, so we don't have to worry about it. So I apologize in advance. If I use them interchangeably, technically I shouldn't, but I will. Again, this lambda here represents the wavelength. D, 589 nanometers, is your standard for this experiment, but you could use a different wavelength if you wanted to, I don't know, be contrary to all the other chemists of the world. Pick a different wavelength and get different values, but you just can't play with their tools because their handbooks, everything else is based on that. Okay, so this is the path length. There's a temp here that I didn't put in, but usually the temperature, we go with standard temperature as well. So I'm just totally ignoring that. Concentration sample, path length, and then observed rotation. So alpha D, as mentioned before, is specifically what we're looking at. Conventions clockwise is said to be positive, but we also say dextrorotatory D. This is going to introduce a new term that we just don't really need. Positive would have been fine, but somewhere along the line they said dextrorotatory and levorotatory. L for levorotatory means it does it counterclockwise. D for positive simply means opposite. Positive means it rotated in the positive direction. Its enantiomer would rotate it in the negative direction. So there's no relationship. Because it goes positive, doesn't mean it's R configuration. Because it goes negative doesn't mean it's S configuration. There was a misnomer because that's what they wanted it to be originally, and about 70–80% of compounds kind of follow that, but it isn't true. There's enough exceptions to the rule that it can be really misleading. So enantiomerically pure, meaning just all of R or all of S, all of one enantiomer, all of the other enantiomer. So let's go back to the ones we did before, the R2-butanol and the S2-butanol. Because it is rotating it counterclockwise, negative, we can also call this, like here are my R and S, we can also call it negative and positive 2-butanol, or we can call it small l, laboratory, or small d. And this is supposed to be a cursive, but it just didn't turn out right, so I've left it as a d. But you'll see it looking more like this, kind of a delta without little hoop up top. Okay, any of these three are fair game. Expect you know this. Reality is, chemists will pretty much only use R and S. Biochemists will use small l or negative, positive L or D. Just because you have to speak both biochemistry and chemistry, you need to know all those terms. Enantiomeric mixture. So here's where it gets sort of interesting. This is how this is useful. So the alpha D that we actually measure for a solution is going to depend on how much R and S we have. So for instance, if we had 100% of the R, we know that a pure sample is negative 35 from what we just did. This is for 2-butanol. If, however, it was all S, so here we're saying R is 100, S is 0. Over here we're saying R is 0, S is 100. Notice it's plus 35. So pure S plus 35, pure R minus 13.5. I think I said it so fast it sounded wrong there. But positive 13.5, negative 13.5. If it's 50-50, you get zero rotation. So if it's half going counterclockwise and half going clockwise, the two cancel each other out. So from this number, we can actually figure out how pure it is. So if it's negative 113.5, it's pure R. If it's positive 13.5, it's pure S. If it's 0, it's called a racemic mixture. Racemic, R-A-C-E-M-I-C. So that word. But if you're somewhere in between, so let's say we get something like that. So over here, I know according to this ratio, it's going to be more R than more S. And how much? Let's say it's 75-25, so I know this value. It's going to be a weighted average of those two. So half of 13.5 is 6.25. 6.75. That's embarrassing, but okay. But negative because it favors R, whereas if you did the one that favored S, so if you got a positive 6.75, you know it would be 25 to 75. This is called enantiomeric excess, meaning you can figure out the ratio from this. Couple ways you can do it. If you're given this number right here, the ratio, and the two numbers add to 100. So if you always do it in percentage, 75 minus 25 is 50. 50% of this one is what this is. 25 minus 75 means 50% in the other direction. So it'd be 50% of this number, which is what we see. Equally, if you know this number and this number, you know this is half as much, then it's half of what it would be that's pure, which means the excess amount of this one isn't 100%. It's half of that. It's 50% excess. 50% excess means 75 and 25. So they differ by 50%. So 50% enantiomeric excess in each case, but in favoring the negative, favoring the positive. So sample with alpha D between 0 and negative 13 must have more R than S, but it is not pure if it is not 13.5. Same thing on the other side. If it's between 0 and positive 13, it must have an excess of an S, but it's not pure S because it's not all the way up to 13.5. Okay, we will be looking at that in a little more detail in some of the homework questions or some of the samples we do. But for now, I just want to toss that concept out there. I'm not going to go incredibly in depth into it, but I fully expect you to understand it when we start talking about racemic mixtures with future reactions. So if a compound has multiple chiral centers, this is where things get a little more convoluted. So everything's been easy, RS, with one chiral center. But if we have two, then you have to take into account other possibilities. So first off, the number of stereoisomers you can get, just to toss this out here, you can have RS at a given stereocenter. So if you have two chiral centers, they both could be R. One could be R, one could be S. One could be S, one could be R, or they could both be S, meaning 4 possibilities. This is mathematical permutation starting to happen. I have 2 possibilities at one center, 2 possibilities at the other. So 2 times 2 means 4 possibilities. So it ends up being 2 to the n. There's 2 possibilities taken n times. 2 centers would be the number of times. That's your maximum number of stereoisomers. And I'm going to put a little caveat here. I'm going to put a little star because we're going to find an exception to the rule in about 2 slides. But for now, this is our rule. The other thing to make note of, if you put a left hand in the mirror, you get a right hand. So if you put two left hands, you'll get two right hands. Or you put right left, you'll get left right, meaning every chiral center changes in a mirror image. So RR and SS are enantiomers because both chiral centers change, RS and SR. And this may not make sense, but if you have two, let's say this is on carbon 2 and this is on carbon 3, then we have to specify. So if 2R goes to 2S and 3S goes to 3R, then both chiral centers change. They are enantiomers of one another. And this is such a cool little looking mirror. I'm quite happy with it. Okay, RR and RS, on the other hand, so if it's 2R going to 2S, that one changed, but 3R going to 3R, no change, and 2R going to 2S, that changed, but 3S staying 3S did not change. So therefore, they are not enantiomers. So they're what's known as diastereomers, a new word to add to your collection. They're not mirror images. So they're not enantiomers. They're going to be called diastereomers. We're going to use that word very shortly. But diastereomers, that didn't come out well, but I liked it at the time. So there's a word. When they're not enantiomers, when stereoisomers differ at one, but not all chiral centers, they're diastereomers. So the easiest way to look at this is decide, are they the same compound? If not, are they enantiomers? If not, by default, they're diastereomers. Diastereomers is the most probable outcome as you get more and more chiral centers. So take these Fisher projections. You have 1, 2, 3 chiral centers in these. So the first one, because you have two switches, keep in mind there are bow ties on these, so if you switch from both sides, that one changed. This one, there, it changed, so it was a reflected center. But this one, not reflected. It's staying identical. So 2 reflected, i.e. they changed, 1 didn't, which means they cannot be mirror images of one another because everything has to reflect. They are what's known as diastereomers. So under the category of stereoisomers, we have enantiomers, mirror images of one another, and we have diastereomers, not mirror images of one another. You'll note not superimposable. If they're superimposable, they are the same compound, meaning if they match identical, if all the parts line up perfectly, same compound. But if they don't line up, that means you have at least one chiral center different. So enantiomers and diastereomers each have to have at least one different. But in the case of enantiomers, all the chiral centers must be different. In the case of diastereomers, not all, some, but not all. So we're going to look at these a couple different ways. So again, the definition, non-superimposable mirror images, non-superimposable and not mirror images, but easier way to say that. So here, mirror image is easy to see. The not mirror image is actually easy to see. So the O's reflect, the 5' ring reflects, but the CH3 is messed up. One's back and one's in front. So it's easy to see that there's not a mirror plane. Here it's easy to see that there is a mirror plane. So if they draw them like that, perfect. But most cases won't be drawn like that. Most will be drawn like this. So this chiral center changed, this chiral center changed. So this went from front to in back, H flipped with it. This CH3 went from back to in front, again, H switched with it. So both of them, all two changed, they're enantiomers. And only some of the chiral centers change. So if I look at this center right here, OH is in front, H is in back, CH3 and the rest of the molecule. CH3 and the rest of the molecule stay the same, but H is in front, OH is in back. So that left chiral center changed. But the right one, notice it's identical. CH3, H, and CH2, CH3, and then the rest of the molecule. So when we say this one didn't change, I know this switch seems like this group changed, but it is just connectivity that we're worried about in this case. So this carbon is connected to things in the exact same manner. CH3 up and to the right slightly, H back, CH2OH out in front, and then the rest of the molecule directly left. Only one chiral center. This one changed, this one did not. Here's where it gets really hard to see, and this is the beauty of just this cool little method. There's no way you can convince me you can rotate this, ring flip it, and do everything you need to do to line it up to see the mirror. It would take you about 5 days to achieve. So instead, we simply note that this is up, down, up. This OH is down, this Cl is now up, this CH3 is down. So it went from up, down, up. When I go OH to Cl to CH3, so up, down, down, meaning every chiral center change, they're enantiomers. And then diastereomers, this center right here changes. This center, no change. So I'm going to have to keep going. I'm done. There's no way it can be an enantiomer. So one change, so it's got to be stereoisomer. So only one changes. And just a little foreshadowing for biochemistry. This is ribose. Ribose is all right. Everything's on the right side. It differs at one carbon, not the first, that's an aldehyde. It differs at the second carbon. So a word you will perhaps see in bio, these are called epimers. They vary at one chiral center in the backbone. So specifically, this would be ribose, just be its C2 epimer. Okay, so not to get a full year ahead of yourself in terms of looking at biochem, but that's where these become very popular. Knowing this relationship, it proves to be very useful in other classes as well. Okay, so enantiomers, all the chiral centers change, diastereomers, some change. So try a little practice, see how it goes. Which of the choices actually describes the relationship of the following stereoisomers? So compound 1 and 2, let's look at those first because that's the first answer choice. Different with the OH, different with the CH3, but the same with this CH3. So different, different, same. 2 change out of 3, so it's some, not all, meaning 1 and 2 are diastereomers. Check, check, out, and check. So we can get rid of choice C by doing this. So again, these, they're diastereomers because different, different, same. So C is gone. Okay, now let's see the next one we go to, compound 1 and 3. Let's see what those are, or 2 and 3. Shoot, I don't know which one to do. Let's do 2 and 3. So 2 and 3, diastereomers. Let's see if this is true. Different, same, same. So 1 out of 3 change, so that's some, not all. So 2 and 3 are considered to be diastereomers. So let's see, that's 1 and 3. That's 1 and 3, so it doesn't matter. Here's 2 and 3. They're not enantiomers. Choice D is gone. Finally, we need to compare 1 and 3. We haven't done that one yet. It's different, different, different. They all change. So 1 and 3 are enantiomers. So 1 and 3 diastereomers. No, 1 and 3 enantiomers. Check. A lot of work to get to this, but the best answer is in beautiful. Hopefully this makes sense and I don't know, somewhat useful. I want to add one more piece of the puzzle, and then we're going to go into a bunch of bio examples, but a meso compound. Before I do anything else, I want you to start with this phrase. I study OChem so much. I'm always sitting in front of my computer working on this with a book, always in the library. I'm just stationary. Me so inactive. Me so sitting around. Me so inactive. So the phrase me so inactive means it does not rotate plane polarized light. So it's optically inactive because me so inactive. Me sits around and just studies. Me so inactive. So they don't rotate plane polarized light, but they have chiral centers. So how can that be? And a good way to think about it, it's almost like they have a built-in racemic mixture within themselves. So half of it is going to do one thing, the other half is going to do the other. So we saw a racemic mixture when it was half and half. You know, if you have one chiral center, it's R, and one chiral center, it's S. That's an example of a meso compound. One half will rotate it one way, one half will rotate it the opposite way. So good example. I'm just sorry, this is typing in everything I've been saying, but a little more slowly. So if I look at this compound, it has a mirror plane right there, so I can see a mirror plane within the molecule, or I can just do R and S. So priority 1, let me go ahead and do this. 2, because it's connected to the side with reaches OH, and 3, H and back, so this will be an R center. Over here, I have priority 1, 2, and 3. So it's an S center, and they are perfectly symmetric. They have the exact same substituents. So because they have the exact same substituents, they're going to exactly cancel each other. So it is optically inactive because it's like a built-in racemic mixture. The R rotates one way, the S rotates the other. They cancel one another. So reflected sides, same thing here, reflected sides. Okay, so a meso compound will not rotate plane propagation light because meso inactive. Meso forgot to put the quote on that side. Okay, so meso inactive, meso compounds are optically inactive. Biological applications, I'm going to move to do this down the road, but we covered a lot of material, and it honestly isn't that hard at face value. When you start getting multiple chiral centers and I start drawing in weird ways like I did with those chair conformations, you can get a little bit daunting. So do not be deceived by the fact that, yeah, it's a straightforward concept. Because where we're really going to run into, I guess, a challenge is when we start looking at chemical reactions and we spit out these products that are chiral, they have optically active or stereogenic centers. We're going to have to distinguish what kind of products we get. And from that, we can deduce what kind of mechanism, how it attacks. So right now, I'm just looking at the flow of arrows. One atom to another atom, one bond to some atom, a lone pair to a bond, or whatever we're looking at. What we will ultimately look at is also, does it attack from right or left, top or bottom? We start getting way more specific about which way those electrons move. And the stereochemistry is going to support that. So thank you for staying so tuned in, and I will see you at the next podcast. So have a great day, and hopefully talk to you soon.